Hello and welcome to my clinic on microcontrollers for model railroading. This is Terry Terrence, but because of ongoing medical problems I'm doing this narration via text-to-speech software. In this clinic we will investigate the many uses for microcontrollers in model railroading. We'll look at the various microcontroller experimenter boards that are available. You may not realize it, but you already use microcontrollers in your model railroading, especially if you use DCC and sound decoders. Each one of these has an embedded microcontroller. What else can you do with a microcontroller? This clinic will explore that question. What will we talk about today? First we'll explain what a microcontroller is, then we'll talk about what it can do for you. Why would I want to do such a thing? We'll talk about making something with a microcontroller. And finally we'll talk about resources you can use. In your desktop computer, a separate microprocessor talks to memory, I/O and other support circuitry. All of these are contained, as distinct entities, on a motherboard. On the other hand, the microcontroller incorporates this, and more, on a single chip. Is it as powerful as your computer? No. But, then again, it's not designed to run spreadsheets or word processors. A microcontroller is, as its name implies, intended to control things in the real world. Is the microcontroller a lightweight? The clock speed of microcontrollers puts them on par with the 286 class processors, back in the day. Whereas the microprocessor in your computer sends out infinitesimal signals, in an attempt to minimize power consumption. The microcontroller's I/O pins can drive small loads, like LEDs. The other integrated peripherals in the microcontroller, like analog to digital converters, timers and pulse width modulation, help you interact with the world beyond the chip. The microcontroller is a single chip, and if we were product designers, that might be all that is needed. But to be useful to a model railroader, more is needed. Things like a power supply and a way to program the chip. The last few years have seen an explosion of hobbyist or engineering boards that operate pretty much standalone. The best known of these are the Arduino family of boards. And, depending on the model, they may incorporate LEDs, switches, touch pads, displays, etc. These boards are the subject of this clinic. When I say microcontroller, I will be referring to one of these boards. What can we build on a model railroad with a microcontroller? Basically all manner of control or animation. This slide illustrates just some of the things that are possible. Many of these have already been built using hobbyist microcontroller boards. The company Backatronics used to produce a line of model railroad effects boards, each of which contained a microcontroller chip. Backatronics gave up their model railroad line a few years back, but, with some ingenuity, every one of their products can be duplicated. Why would I want to roll my own when I can just buy a commercial product? Cost is one consideration. You may also want a function not offered by any manufacturer. As alluded to with the reference to Backatronics, mom and pop businesses in our hobby close-up shop all of the time. And finally, getting this stuff to work is cool, and your buddies will think so too. Let's look at some cost comparisons. We'll look at the cost of a commercial crossing detector and flasher versus rolling your own. For the commercial product we'll use Circuitron's DF1 detector and flasher at $44.95. To roll your own will require a microcontroller. We've assigned a price of $9.99 for this item. As we'll see, it could be less, but $9.99 is towards the top of the range. About $2 for two IR LEDs, similarly $2 for a pair of photodiodes. These form the train detector. Software for the microcontroller is free, either generated by you or downloaded from a website. The total cost of do-it-yourself is about $14. The microcontroller has more than enough horsepower to monitor a couple of train detectors, one east and one west or north and south, and flash the lights when either beam is intercepted. The software inside the microcontroller can be set up to detect trains approaching from either direction. The commercial product is unidirectional. Want to detect in either direction? That costs more. For my second example, let's see what it costs to reproduce Circuitron's AW2 arc welder simulator. The commercial product is $29.95. To roll your own will cost $9.99 for the microcontroller board and about 50 cents for a pair of white LEDs. Software, per usual, is free. For about $10.50 total. Now, I'm not beating up on Circuitron. If you need only one or two effects or animations, and a commercial vendor make the effect, it probably does not pay to learn microcontrollers. But what if you want to have signals on your whole layout? It could get expensive fast. Or what if the effects that you desire is not available commercially? The next slide will address this situation. I'm a B&O modeler. B&O CPL signals have 4 main indications and up to 6 markers, 3 above and 3 below. There can be up to 37 distinct indications, including flashing modes. It's unlikely that any commercial manufacturer will produce a signal controller that can reproduce all of these indications. However, it's possible to program a microcontroller to do so. Everyone's yard is different, with a varying number of storage tracks and through tracks. Yard routing had heretofore been done with things like diode matrices. A microcontroller can handle yard routing of arbitrary complexity, limited only by the number of output pins for the switch machines. Every interlocking situation is unique. Some modelers have built mechanical interlocking machines that function like the prototype. These are wonders and can be the focus of the layout. However, if all that you wish to accomplish is to keep the trains from crashing, then having a microcontroller running your interlocking might be just the ticket. And, it's much easier to correct logical mistakes in software than it is to do the same in a system of levers. By now, everyone has seen the animation where a blacksmith is pounding his anvil while occasionally turning his head to the side. It's fascinating, for a while. Eventually you pick up the repeating pattern and realize it's not that sophisticated. Would you prefer to have a complex animation, even one with random movements or actions that proceed partway, stop, and then reverse? It's all possible with a microcontroller. Do you have a city on your layout? Do you want the lights to come on and go off in your buildings in a realistic pattern that mimics habitation? I'm not talking about Lionel-style lighting here that comes on full glare and shuts off just as abruptly, but an ever-changing pattern which can even duplicate the fade-out of an incandescent filament? What about chase lights on a theater? Or blinking neon signs? Child's play for a microcontroller. In fact, it could do several effects at once. I referenced Backatronics before as an example of an electronics manufacturer who had left the model railroad market. Manufacturers leaving the model railroad space is a well-known phenomenon to modelers. Microcontrollers, as well as laser cutting and 3D printing, can fuel a small-scale, do-it-yourself, on-demand manufacturing movement. That does not mean that each individual needs to become adept at all of these skills. But familiarity with at least one will be helpful. At its best, such a movement might become what the software geeks call open source, where all designs are published and are free for anyone to use, non-commercially at least. Better still, the movement might become crowd-sourced whereby talented people contribute their skills to the group's project. No doubt about it, programming a microcontroller, and building a microcontroller project is cool. Like 3D printing, this is creating at a very basic level. We may be able to attract tech-savvy young folk to the hobby if we can show some high-tech elements to it. The prices and availability of microcontroller boards was correct at the time that I gave this clinic, 2016. I have not updated price, nor features or availability to this year, 2022. So be advised. The selection criteria are still valid, with the exception of the last one, which will be discussed later. The Arduino family has not waned in popularity in the years since 2016. The family of Arduinos has grown with boards at many capabilities and price points. Because Arduino is open source, it can be produced by many different companies, leading to wide divergence in price and quality. You need not pay top dollar for an Arduino. One sold by a mass merchandiser might represent the best value. Do not discount the value of the user base for the Arduino. In addition to add-on boards and code examples, help is usually a forum post away. TI's LaunchPad is where I started my journey with microcontrollers and model railroading, largely because the introductory price was $4.30 shipped from TI. Several people and I developed several model railroading projects for the LaunchPad. They can be found on the blog. Middling in capabilities and price compared to the best Arduinos and all of the Raspberry Pis, the LaunchPad is still worthy of a look. Freescale's Freedom family of microcontroller boards is the first in this review to utilize the ARM processor rather than a proprietary chip. Does this make a difference to the end user? Not really. ARM processors are a lot more powerful, but that power is extraneous for our purposes. Some of the Freedom family are hardware compatible with Arduino add-on boards, and it may make sense to select these boards when using them for model railroads. Freedom boards must be programmed with their own tools. I doubt that they can run Arduino programs, called sketches in Arduino speak. Freedom boards were available from the electronics distributors, for instance DigiKey or Mouser. Watch prices, sometimes these distributors add their own markups. Coming in at a lower price than the Freedom boards is ST Microelectronics Discovery family. Discovery boards also use an ARM processor, and also must be programmed with their own tools. As far as I know, unless something has changed since 2016, none of the Discovery boards are Arduino compatible. Some versions of the Discovery boards have displays on them, so if you need a human-readable interface, these might be your choice. DigiStump's DigiSpark is somewhat unique in that it was crowdfunded. Because of the crowdfunding, DigiSpark is one of the least expensive microcontroller boards. Every expedient is used to reduce costs, as the USB interface formed on the PCB illustrates. There are a number of add-on boards for this tiny, inexpensive microcontroller. The chip selected for DigiSpark has PWM built in which, when combined with an available motor driver add-on board, should make mechanical animation easy. Access to the limited number of output pins is via pads on board, barely visible in the photo. Cypress Semiconductor's CY8CAD949-4200, gosh, what a name, was, in 2016 the low price leader at $4. Yes, in 2016, I did buy a couple at this price. I doubt that this price has held 6 years later. The programming section, including the onboard USB interface, left, can be broken off once the board is programmed and tested. 39 I/O lines and an ARM processor makes this board one of the best for lighting animations and, possibly, for signal animation because it has the power and I/O to handle multiple blocks at once. Now we come to the Raspberry Pi. The Raspberry Pi uses a system on a chip, much like the one in your cell phone. It also has circuitry to produce a video output. It is a full computer on the card. Because of this, it requires a keyboard and a monitor, as well as an operating system to program it. Plus the initial price of $25 made it too expensive to build into model railroad projects and put it outside my selection criteria. All of that changed with the introduction of the Raspberry Pi Zero, pictured, and the Raspberry Pi Zero W, for wireless. The Raspberry Pi Zero's introductory price was $5. The Zero W was a couple of dollars more. Due to high demand, and the chip shortage, it's still hard to find them at this price. But I found some, in onesie quantities, at $5. The Raspberry Pi Zero W, at anywhere near the list price, opens up the prospect of wireless layout control. Conceivably, it could eliminate tons of wiring below the layout. Imagine layout command control passed wirelessly from node to node. Because all Raspberry Pis boot from a micro SD card, providing pre-programmed micro SD cards takes care of any programming issues. This deserves further investigation. How do you design a project with a microcontroller? First pick, or conceive, a project. Pick a microcontroller, more on this later. Add external components, these will almost always be necessary. Write or download a program to program your microcontroller. Provide power to your microcontroller board, as well as the rest of your project. A subsequent slide will address this. Finally, admire your handiwork. Even a simple flashing LED can be a triumph your first time. If you know what you are doing, you can design your own project using LEDs, relays, motors and servos. Don't know what you're doing? Don't worry, you'll pick it up quickly. One method is to find projects on the web, figure out how they are doing it, keep the snippets of code and parts of circuits that you need for your project. Ask questions on the forums, many people are glad to help a newbie. Almost all of the microcontrollers provide code, that is software, to blink the onboard LED. Look at this code, it's simple but it will give you a start. You'll also learn to use the toolset to load your microcontroller. Remember, all software, including the most complex, is built out of smaller snippets of code. There are books devoted to microcontrollers in general, and for specific microcontrollers, for instance the Arduinos. Or you may be able to find a project that you need on the internet. The robotics forums may be ripe to find mechanical animation projects. Finally, there are some pre-packaged projects, enough to get your feet wet, for the LaunchPad at the blog on this slide. I started the LaunchPad for model railroading blog when I was experimenting with the LaunchPads. This was back in the day when LaunchPads were inexpensive and before other alternatives were available. The code examples could be adapted to other microcontrollers. The code is written in the standard C programming language, and may not be as easy to follow as an Arduino sketch. The blog has not been updated in many years, so it is what it is. A version of the MSP 430 LaunchPad is still available from TI, so these projects may still be usable. Which microcontroller should you choose? If you are using a pre-canned project, then the choice is simple, use the microcontroller specified. If you are starting from scratch, or just want to learn about microcontrollers, pick the Arduino. It's readily available, inexpensive, and the online support in the form of projects, tutorials and forums can't be beat. The toolset used to create sketches is feature-rich. If you need a lot of microcontrollers, for example, to implement a signal system or for switch machines, then cost may become a consideration. In addition, special features, as noted on this slide, might drive your decision. Most of the major electronics suppliers stock hobbyist microcontroller boards. Shop around for price. The price can vary widely between the various suppliers. Some of the manufacturers, TI for instance, sell direct. If you have a Micro Center store nearby, you are in luck. They stock Arduinos and, occasionally, they have hard to find Raspberry Pis, including the Raspberry Pi Zero W, often at discount. Unfortunately, they generally will not ship the discounted microcontrollers, reserving them as in-store loss leaders. If your project involves LEDs, they can be wired directly to the microcontroller's output pins. Don't forget to use a 270 to 300 ohm resistor in series to limit the current. Incandescent lamps of up to 25 mA can be driven directly as well. Remember, I/O pins are only 3.3 to 5 volts, your lamps need to be low voltage as well as low current. If your current or voltage requirements are more than this, maybe you can find an auxiliary plug-in board compatible with your microcontroller. These are called shields for the Arduino, booster packs for the LaunchPad, and hats for the Raspberry Pi series. Other microcontrollers have their own terminology for add-on boards. These boards provide a number of different functions to the underlying microcontroller. If you still cannot find an add-on board to suit your project, you might look into some of the universal modules we will talk about on the next slide. This illustrates just some of what is available in auxiliary modules that you can use with your microcontroller, regardless of make or model. These will interface to any microcontroller because they use a 3-wire interface. Power, ground and signal. Power and ground are self-explanatory. Do note that many of these modules operate on a 5-volt supply, A regulated 5 volts. When the signal goes low, that is, goes to ground potential, the module activates. If the module is an input device, say an optical detector, the signal line going low indicates that the input has been tripped. This behavior is called active low. Starting in the upper left-hand corner are some relay modules. These can be had in 1, 2, 4, 8, even 12 relays per. These modules are an exception to the rule that these modules operate on 5 volts. They come in 5 volt and 12 volt varieties, maybe more than that. For interfacing to a microcontroller, choose the 5 volt variety. Also watch the rating of the relay contacts, in most cases they can handle more amps than you are likely to use on a model railroad. Next up is a keypad. The keypad is an exception to the 3-wire interface rule. Most keypads are matrixed, that is there's output pin for every row and every column. Your microcontroller must be configured for as many input pins. When a key is pressed, that row and that column will go low, and your microcontroller can interpret whatever letter, number or function assigned has been activated. Upper right are optical sensors. These are generally infrared devices and, generally, use a 38 kHz modulation on the signal to prevent jamming by infrared light sources like the sun and incandescent lights. But this feature is not universal, as I found out to my chagrin one day. By the way, if you want to see whether the light is on, your cell phone camera can see infrared light, use it as a detector. When the optical detector trips, the signal line goes to ground. In the lower right are motor drivers. In the case of these modules, the signal line is pulse width modulated by your microcontroller. The power and ground lines are the power that you are going to provide to the motor under power. You have to make sure that the current capacity of the module is at least as high as the motor you wish to power. By the way, the large board, lower right, has a capacity of 6 amps. The picture in the center is a LaunchPad, because I borrowed this slide from my LaunchPad presentation. These modules operate at various voltages and current levels. This will all work if there is a common ground between them. Tie all of the grounds together, including your microcontroller, with at least one wire. The electrons know where they started and where they are going and will sort themselves out. One other potential pitfall that you might want to watch out for, electronics engineers call this Fanout. This bit me in the butt on one of my modules, and I should know better. A output pin should only drive 2 to 3 loads no more, or you get into Fanout trouble. You can obtain these modules on eBay or directly from Chinese suppliers, like Deal Extreme, Banggood or Alibaba. If you buy directly from China, always pay with PayPal, this way the Chinese supplier never sees your credit card information. These modules are not expensive, most of the time for lower cost than you can buy the components for. You will need to download and load the toolset provided by your microcontroller provider onto your PC. The toolset will allow you to compile code for your chosen microcontroller and then load the machine-readable instructions into your microcontroller. All of the hobbyist microcontroller boards will connect to your PC via USB. You will not need to know the details of where or how to load your microcontroller, all of this should be taken care of by the toolset. If this is confusing to you, have a buddy, or maybe your kid, to show you how. By far, the easiest way to power your microcontroller is via the onboard USB port. Some will utilize a full-size USB plug, others will use a micro USB. If you are just powering 1 or 2 microcontrollers, you probably have an unused phone charger or 2 that can be pressed into service. For powering more than a couple of microcontrollers, my suggestion would be to use a powered USB hub. Through the use of USB extension and USB to micro USB cables, both available at the dollar store, you can power several microcontrollers spread throughout your layout. For truly large layouts, the runs to reach all of your microcontrollers may be too far, so a second powered hub may be necessary. The next slide will illustrate a powered USB hub. If you have a source of regulated, and I emphasize regulated, 3.3 or 5 volt DC, you can power most microcontrollers directly. This will require soldering to pads on the device, and proper polarity must be observed. I am compelled to emphasize that supplying dirty power to a microcontroller can destroy the device. It will likely not result in smoked components, but operation will be affected. This is a USB-powered hub. This particular brand and model is not a good choice. The sockets do not hold the USB plugs tightly. This powered hub has a single switch to turn off the power. Other powered hubs have switches for each individual port. Some, especially small hubs, have no power switches. My resource section begins here. I will present this without commentary until we get to the last slide. Feel free to pause the video wherever you need to. Let's take a moment to say a word about hackerspaces. Hackerspaces, also referred to as hack labs, makerspace or hackspace, are labs or studios incorporating elements of machine shops, electronic labs and more. Open to all comers, sometimes free, but more often via dues. While most concentrate on robotics, all manner of high-tech projects are undertaken, like sending balloons to the edge of space. They usually have lots of people versed in microcontrollers. They will probably advise you on your project without paying any dues, especially if you do not need access to their facilities. Most major cities have a hackerspace. Use Google to find one near you. Show up at one of their meetings to see what your nearest hackspace is all about. Hack DC, where I went a few times, had a regular meeting titled Microcontroller Monday. One word of caution. Remember, you are going into their world. While you may be thinking, you think that by making small robots you're going to change the world? They are thinking, why is a grown man playing with miniature trains? Thank you for viewing this video to the end. If you have questions, ask them in the comments. I'll try to answer all questions.